Welcome back. We're going to talk today about limits at infinity. I'd prefer it be called limits as x approaches infinity, but that's probably too long of a title. So we're going to talk about that today. What I'd like you to do is grab a calculator. If you don't have one, go get one. And we're going to look at some graphs. So I'd like you to set your window on your graphing calculator to have x go from negative 50 to 50 by steps of 5. And your y's go from negative 10 to 10 by steps of 1. Okay, if you don't know how to do that, maybe call a friend or something like that and have them help you set it up. Once you've done that, I've got 3 functions listed here. I'd like you to graph each one of them separately and match each one up with a description of what happens as x approaches infinity over here. Now when I say x approaches infinity, we're looking at what happens to the graph as you go very, very far to the right. So as x gets really, really big, that means the graph is going off to the right. So what happens when you do go off to the right? One of 3 things is going to happen. Each one of these is going to match up with one of these. Either the graph is going to approach a horizontal asymptote of 0, or the graph is going to approach a horizontal asymptote of 4.5, or the graph is not going to approach a horizontal asymptote at all. So take some time, graph each one of those, pause the video, and then when you resume the video, we'll talk about what was what. All right, welcome back. Hopefully you got some good graphs. Let's see what the graphs look like. Here's f of x. All right. Looks like it's got like a nice little high hill in the middle, and what you'll notice as the graph goes off to the right, there is a horizontal asymptote of y equals 0. So this one goes with this one. All right, let's look at the second one. That's what it looks like. Looks like almost a parabola there. So as the graph goes off to the right, it really doesn't approach a horizontal asymptote at all. So we can say that this graph here goes with that description down there. And so it's pretty obvious what the last one's going to do. Here's the graph, and you can see that as it goes off to the right, it approaches a horizontal asymptote of y equals 4.5. So that is this one right here. So hopefully you got the same things. If not, go back and try this exercise again and see, maybe there was some parentheses in the wrong place or something. But let's talk about why any one of those 3 things happens. All right? Well, I gave you an example of each one of these 3 things. One of the functions had a degree on top that was bigger than the degree on the bottom. And that was the one where there was no horizontal asymptote. Okay? We could talk later about what a slant asymptote is, or even a parabolic asymptote, and they actually can get worse than that. So, but the main thing is that there really isn't a horizontal asymptote that those functions approach. Another example I gave was where the degree on top was lower than the degree on the bottom, which meant that the horizontal asymptote was y equals 0. And when the degrees were equal, the horizontal asymptote actually ended up being the ratio of the lead coefficients. So there's a lot of terminology I'm throwing at you. Make sure you take some time and understand all these words that I'm saying, because we are going to move on. So I want to talk about why that happens. We can't really substitute. When we're talking about limits, remember one of the strategies was you could plug in the value of x that x is approaching. But you can't plug in infinity into an expression. It's not really a number. It's just the concept of being really, really big. But what we do know is that as x approaches infinity, 1 over x approaches 0, right? That makes sense. And by the same logic, 1 over x squared, 1 over x cubed, 1 over x to the 4th, all of those approach 0. So if I had those kind of terms in my function, then I would be able to plug in something a lot more easily. So let's do that. What we're going to do every time we get one of these functions that is a fractional function, I am going to divide every term in the numerator and in the denominator by the highest power of x. So looking at the first function, and I believe I called this f of x, I've got some x's on top and a constant. I've got x squareds on the bottom and a constant. So what I'm going to do is I'm going to divide everything by the highest exponent of x, which is x squared. So let me do that. So I take this, and my 2x gets divided by x squared, 13 gets divided by x squared, x squared gets divided by x squared, and 2 gets divided by x squared. I can do that because I'm dividing top and bottom of the fraction by the exact same thing. All right. 2x over x squared, well, this x can cancel with one of these x's, so it actually behaves a lot like 2 over x, which we said approaches 0. And 13 over x squared also approaches 0 as x gets really, really big. X squared over x squared, though, those two things cancel out, so you're left with 1. And 2 over x squared approaches 0. So what I've got is 0 plus 0, which is 0, over 1 plus 0, which is 1, so I get a limit of 0. So this has a horizontal asymptote of y equals 0, because that's what happens as your x's get really, really big and approach infinity. Let's look at the second example. Same thing. I've got x cubed and x's and more x's and a constant. So I'm going to divide every term by the highest exponent of x, which is x to the third. So x to the third gets divided by x to the third. 3x gets divided by x to the third. 15x, sorry about my sloppiness, gets divided by x to the third. And 8 gets divided by x to the third. And that's a little out of line, but you get the idea. X to the third over x to the third, those cancel, giving me 1. 3x over x to the third, well, that x on top can cancel out with one of those in the bottom, giving me 3 over x squared. And 15x, that x can cancel with one of those x's, giving me x squared on the bottom, and then 8 over x cubed can't be simplified. So the 1 I just copy. 3 over x squared becomes 0 as x gets really big. Same with 15 over x squared, that approaches 0 as x gets really big, and 8 over x cubed approaches 0 as x gets really big. So what I have is I have a 1 on the top and I have a 0 on the bottom, and that is undefined. So there is no horizontal asymptote. And then moving on to the last one, which I called h of x. I've got 9x plus 11 over 2x plus 1. And so the highest exponent of x I have is x to the 1. So I'm going to divide every term by x to the 1. 9x becomes 9x over x. 11 over x. 2x becomes 2x over x. And 1 becomes 1 over x. All right. Well, the x's cancel here, leaving me with just 9. Nothing cancels here. These x's cancel out, leaving me with just 2, and nothing cancels here. So I've got a 9, which I copy here. 11 over x approaches 0. 2 gets copied down here, and 1 over x approaches 0. So what I've got is I've got a 9 on the top and a 2 on the bottom. And what you'll notice is those two numbers are the lead coefficients of the top, or they were the lead coefficients of the top and the bottom of my original function, and that is 4.5. Okay, so those three are the only three things that'll happen. Either there will be a horizontal asymptote of 0, a horizontal asymptote of the lead coefficients, or no horizontal asymptote at all. And you need to know when those happen so you can do these problems a lot quicker. All right, it is your turn. You need to find the following limits. Again, it's the same kind of question. So pause the video, take some time and solve these problems, and then when you resume, we'll talk about the answers. All right, well, what you should have found is that this is one of those situations where the degrees on top and bottom are the same. So the limit as x approaches infinity is just the quotient of the lead coefficients, which is 2/3. In the second example, the degree on top is higher than the degree on the bottom, so there will not be a horizontal asymptote. And then in the third example, the degree on the bottom is bigger than the degree on the top, so the horizontal asymptote is 0. All right, and we'll do more of those examples in class. Remember, email me a question, ask me a question of some kind. Again, there's really not much practical application of this, not until we hit calculus pretty hard. So try not to ask that question because the answer is there's really no practical application of this. So we'll talk about this more in class tomorrow.